This webcast continues Worksheet 8D on energy conservation diagrams. We're going to look at problems 2 and 3. Okay, in problem 2, we have a situation of a car that's rolling up a hill. The car's engine is turned off, so there is no power, The only reason the car is moving is because it had attained a fast speed and it hasn't slowed down to a stop yet. And it's telling us that there's no friction. Okay, so no friction and there's no power on the car. And it tells us to consider a system that has the car, the road, and the earth. Okay, so at the beginning, the car is on the ground, so it doesn't have any height yet, and it's moving. At the end, the car is higher, and it has stopped. So it's not moving anymore. Okay. So I have to consider what kind of energy does this car and its system have at position A. I'm going to just go ahead and put all of the categories of energy that we've been talking about so I can consider them one at a time. So I know that it is on the ground, so there must not be any gravitational potential energy. It's moving, so it does have kinetic energy. There's nothing in this system that can have a reversible deformation, therefore there's no elastic potential energy, and we never show dissipated energy in the first view. So all of its energy at the beginning is stored as kinetic energy. And then at the end of, at position B, the car has rolled up a hill, so it definitely has gravitational potential energy now because it is a much higher position above the ground. And it stopped, so there is no more kinetic energy. And there was no friction, so there's no dissipated energy. So at the end, all of its energy is stored as gravitational potential energy. So my conservation equation says that all the energy at the initial condition, which was kinetic energy, has now been redistributed, and it is all stored now as gravitational potential energy. Okay, let's go on to part 2B, which is the same situation, except now there is friction. So our system is the car, the road, and the earth. And again, at the beginning, all of the energy is kinetic energy because it is on the ground. At a height of 0, but it's going fast. And at the end, it is much higher. So I have gravitational energy. I have no kinetic energy anymore. And now that there is friction, that was our change, there is friction, I need to allow for some of my energy to get transferred into the dissipated energy category. And so I guess that means that I have less height. There must be less gravitational potential energy here at position B. That's because I only had 5 blocks of energy to start with, right? And then those 5 blocks of energy got redistributed between gravitational energy and dissipated energy at the end. The conservation equation would be that the change in the kinetic energy is equal to the change in the gravitational potential energy plus the change in the dissipated energy. Okay, let's go on to problem 3. So here we have another car, but now it's a person who's pushing the car, and the parking brake is on. They're really making the job hard. That tells us there is friction. And we're going to assume that the system includes the car, the road, and the earth, but does not include the person. Okay? So a person has chemical energy, right? And so I'm not going to show any chemical energy. At the beginning, the car is at rest. They're telling me V is 0, and it's on the ground. And then at position B, it's at rest. And I'm saying that because they're telling me the velocity there is 0, but it's at a higher position. So if I think about, the various types of mechanical energy, at the beginning, it has no gravitational energy. It's on the ground. It has no kinetic energy. It's not moving. No elastic energy. No dissipated energy. Oh, okay. There's really no mechanical energy at the beginning. But at the end, it's much higher, so it definitely has gravitational potential energy. There's no kinetic energy since it's not moving. And there might be some dissipated because of that parking brake. So I'm going to put some dissipated energy, and it's definitely higher than it was, so it has gravitational energy now. Where did that energy come from? It came from the person. The person, poor thing, look at them, they're exhausted at the end. They're laying on the ground. They're not dead, but they're just very tired because they have pushed this car with the parking brake on up this hill. And so they did work. They applied a force and they caused a displacement. And those are the two criteria for doing work. And so our conservation equation becomes the work equals the change in the gravitational energy plus the change in the dissipated energy. Okay, let's look. I think they have another version of this, part B of number 3. It said now the person is in the system. Okay, that's the change. Now it includes the person. Okay, so we've got the car, the road, the earth, and the person. So now there is some energy at the beginning because that person has chemical energy, from the breakfast they ate or whatever. And at the end, the person has much less chemical energy. The car is much higher, and there was some dissipated. And so I don't want to show maybe 0 chemical energy, but I'm just going to show a little. And mostly what we have is gravitational potential energy because the car is now up at the top of that hill. Since the chemical energy is on both sides of my conservation diagram, I need to use little subscripts to say that, to differentiate. So I have my initial chemical energy equals the final chemical energy plus the change in the gravitational potential energy plus the change in the dissipated energy. Okay, because I have to show that the energy in this system at position A still equals the energy at position B because this is an isolated system. There was no interactions with other external systems. Okay, thank you.